7 Powerful function of capacitor and its application. A capacitor is a fundamental component in electronics that stores electrical energy in an electric field. Here are 7 powerful functions of capacitors and their applications. Energy storage is one of the primary functions of capacitors, and it's a critical aspect in various applications. Here's a deeper look into how capacitors store energy and where this function is applied. How capacitors store energy. Principle. Capacitors store electrical energy by accumulating charge on their plates when a voltage is applied across them. The amount of energy a capacitor can store depends on its capacitance, measured in farads, and the voltage applied. The energy stored in a capacitor is given by the formula equals 1, 2, 2, E equals 2, 1, CV, 2, where E is the energy stored in joules, C is the capacitance in farads, V is the voltage across the capacitor in volts. Applications of capacitors for energy storage. Backup power supplies, uninterruptible power supplies, UPS. Description. Capacitors provide temporary power during short outages or when switching from one power source to another. Example. In computers, capacitors help prevent data loss by maintaining power during brief interruptions. Flash photography. Description. Capacitors store energy and release it in a quick burst to produce a bright flash. Example. The flash in cameras is powered by a capacitor that discharges rapidly to create a bright light. Power conditioning. Description. Capacitors store energy to smooth out fluctuations in power supply, providing a steady voltage output. Example. In renewable energy systems like solar panels, capacitors help manage the variability in power generation by storing excess energy and releasing it when needed. Electric vehicles, EVs. Description. Capacitors, often supercapacitors, store energy for rapid charging and discharging, complementing batteries. Example. Supercapacitors in EVs provide quick bursts of power for acceleration and capture energy during regenerative braking. Pulse power applications. Description. Capacitors provide high-energy pulses in applications requiring short, intense bursts of energy. Example. In medical defibrillators, capacitors store energy and release it rapidly to deliver the shock needed to restart a patient's heart. Energy harvesting systems. Description. Capacitors store small amounts of energy collected from ambient sources like vibrations, heat, or light. Example. In wireless sensors, energy harvested from the environment is stored in capacitors, providing power for operation. Memory backup in electronics. Description. Capacitors provide temporary power to volatile memory systems during power interruptions. Example. In SRAM, static RAM, modules, capacitors maintain the stored data for a brief period after the main power is lost, allowing time for data to be saved. Advantages of capacitors for energy storage. Fast charging and discharging. Capacitors charge and discharge much faster than batteries, making them ideal for applications requiring quick energy release. Long life cycle. Capacitors can go through millions of charge-discharge cycles without significant degradation, unlike batteries. High power density. Capacitors can deliver a lot of power in a short time, which is crucial in applications like electric vehicle acceleration or power tools. In summary, capacitors are essential in energy storage applications where quick charge/discharge cycles, longevity, and high power density are required. They complement other energy storage technologies, such as batteries, in various electronic and electrical systems. Filtering is a crucial function of capacitors, and it's widely used in electronic circuits to manage signals and power supplies. Here's a detailed look at how capacitors are used for filtering in the various applications. How capacitors filter signals. Principle. Capacitors block DC, direct current, while allowing AC, alternating current, signals to pass through. This property is used to filter out unwanted noise or signals from a circuit. In filtering applications, capacitors are often used in combination with resistors or inductors to create filters that allow certain frequencies to pass while attenuating others. Types of filters. Low-pass filters allow low-frequency signals to pass through while blocking higher-frequency signals. High-pass filters allow high-frequency signals to pass through while blocking lower-frequency signals. Bandpass filters allow signals within a specific frequency range to pass through while blocking signals outside this range. Bandstop filters block signals within a specific frequency range while allowing signals outside this range to pass through. Applications of capacitors in filtering. Power supply smoothing. Description: capacitors smooth out fluctuations and ripples in DC power supplies by filtering out AC noise. Example: in power adapters, capacitors are used to stabilize the output voltage and reduce noise, providing a clean power supply for sensitive electronic components. Signal conditioning in audio systems. Description: capacitors filter out unwanted noise or hum from audio signals, ensuring clear sound quality. Example: in audio amplifiers, capacitors remove low-frequency noise or high-frequency interference, improving sound clarity and fidelity. Radio frequency (RF) applications. Description: capacitors are used in RF circuits to filter specific frequencies and tune the circuit to desired channels or frequencies. Example: in radio receivers and transmitters, capacitors in tuning circuits select and filter specific RF signals for better reception and transmission. Decoupling and bypassing. Description: capacitors are placed near power pins of integrated circuits, ICs, to filter out high-frequency noise and stabilize the voltage supply. Example: in digital circuits, decoupling capacitors prevent power supply noise from affecting the operation of logic chips and microcontrollers. Crossovers and loudspeakers. Description: capacitors are used in crossover networks to direct different frequency ranges to appropriate speaker drivers, e.g., tweeters, mid-range, woofers. Example: in a three-way speaker system, capacitors filter high frequencies to the tweeter and low frequencies to the woofer, ensuring each driver handles the frequencies it's designed for. Filtering in communication systems. Description: capacitors filter out unwanted frequencies and noise from communication signals, ensuring clear and reliable transmission. Example: in cellular base stations and network equipment, capacitors help filter out interference and ensure signal integrity. Noise reduction in power electronics. Description: capacitors filter electromagnetic interference, EMI, and radio frequency interference, RFI, in power electronic circuits. Example: in switching power supplies, capacitors reduce EMI and RFI, protecting sensitive components and improving overall performance. Advantages of using capacitors for filtering. Frequency selectivity. Capacitors can be easily adjusted to filter specific frequency ranges, making them versatile in various filtering applications. Low insertion loss. Capacitors have minimal impact on the desired signal, ensuring that the filtered signal retains its quality. Compact size. Capacitors are relatively small components, allowing for compact filter designs in electronic devices. In summary, capacitors play a vital role in filtering applications by managing and improving signal quality and stability in various electronic systems. They help in smoothing power supplies, conditioning audio signals, tuning radio frequencies, and reducing noise, contributing to the overall performance and reliability of electronic devices. Timing is a crucial application of capacitors in electronic circuits. Capacitors, often combined with resistors or other components, can create precise timing elements. Here's a detailed look at how capacitors are used for timing and their applications. How capacitors are used for timing. Principle: capacitors charge and discharge at predictable rates determined by their capacitance and the resistance in the circuit. This characteristic allows them to be used in timing circuits where precise intervals are required. The time constant, tau, of a capacitor resistor RC circuit is given by tau equals times tau equals or times C, where tau is the time constant in seconds, R is the resistance in ohms, C is the capacitance in farads. The time constant represents the time it takes for the voltage across the capacitor to reach approximately 63.2% of its final value during charging or decay to 36.8% during discharging. Applications of capacitors in timing. Oscillators. Description: capacitors, in combination with resistors and inductors, form oscillators that generate periodic waveforms such as sine waves or square waves. Example: in quartz oscillators, capacitors help stabilize the frequency of the oscillator, which is crucial for accurate timekeeping in watches and frequency generation in communication devices. Timer circuits. Description. Capacitors, along with resistors, create circuits that generate time delays or produce precise timing intervals. Example. In 555 timer ICs, capacitors are used to set the timing interval for generating pulses or time delays, which can be used in various applications such as blinking LEDs or pulse width modulation, PWM, signals. Pulse generators. Description. Capacitors are used to create short, precise pulses in electronic circuits. Example. In pulse generators, capacitors determine the width and timing of the pulses used for digital signal processing or synchronization in digital systems. Frequency dividers. Description. Capacitors in conjunction with other components can be used to divide the frequency of an input signal. Example. In digital clocks, capacitors help divide the high-frequency oscillator signal to produce the lower frequencies needed for timekeeping. Time delay circuits. Description. Capacitors provide a delay before an event occurs by charging up to a specific voltage level. Example. In relays or timers, capacitors create a delay before activating the relay or triggering an event, such as turning on a light after a delay. Flashing LED circuits. Description. Capacitors control the timing for the on-off cycles of LEDs, creating flashing or blinking effects. Example. In decorative lights or indicators, capacitors are used to set the blink rate of LEDs for visual effects. Debouncing switches. Description. Capacitors are used in circuits to eliminate the noise and bouncing effects when a mechanical switch is pressed or released. Example. In microcontroller input circuits, capacitors help stabilize the signal from switches, preventing multiple false triggers caused by mechanical vibrations. Advantages of capacitors in timing circuits. Precision. Capacitors can be chosen with specific values to achieve precise timing intervals, making them suitable for accurate timing applications. Simplicity. Timing circuits using capacitors and resistors are relatively simple to design and implement. Adjustability. The timing interval can be adjusted by changing the values of the capacitors and resistors, allowing flexibility in circuit design. In summary, capacitors play a critical role in timing applications by providing precise control over intervals and delays in electronic circuits. Their ability to charge and discharge at predictable rates makes them essential for creating oscillators, timers, pulse generators, and other timing-related functions. Coupling and decoupling are essential functions of capacitors in electronic circuits. They help manage signal integrity and stabilize power supplies, ensuring reliable operation of electronic devices. Here's a detailed look at each function. Coupling. Function. Description. Coupling capacitors are used to pass AC signals between different stages of a circuit while blocking DC components. This allows for the transmission of varying signals from one part of a circuit to another without affecting the DC bias conditions. How it works. Principle. Capacitors allow AC signals to pass through while blocking DC components. The impedance of a capacitor decreases with increasing frequency, making it an effective coupling device for AC signals. Application. In coupling applications, capacitors are placed in series with the signal path to block DC while allowing AC signals to transfer. Applications. Audio amplifiers. Coupling capacitors pass audio signals from one stage of the amplifier to the next while preventing DC bias from affecting subsequent stages. Example. In a multi-stage audio amplifier, coupling capacitors ensure that each stage receives the correct audio signal without interference from DC voltages. Signal processing. Coupling capacitors are used to connect different signal processing stages in analog circuits, such as mixers or filters, while maintaining proper signal integrity. Example. In a radio receiver, coupling capacitors transfer the modulated signal through various stages of demodulation and amplification. Transistor circuits. Coupling capacitors are used in transistor amplifiers to connect the input signal to the base and the output signal from the collector while blocking DC bias. Example. In a common emitter amplifier, coupling capacitors allow the AC signal to reach the transistor's base while isolating the DC bias from the signal source. Decoupling. Function. Description. Decoupling capacitors are used to stabilize the power supply voltage by filtering out high-frequency noise and transients. They provide a local reservoir of charge to smooth out fluctuations and prevent interference from affecting sensitive components. How it works. Principle. Decoupling capacitors act as a filter by providing a low impedance path to ground for high-frequency noise and transient signals. This helps maintain a stable DC voltage for the circuit. Application: decoupling capacitors are placed close to power pins of integrated circuits, ICs, to reduce noise and stabilize the voltage supply. Applications: power supply filtering. Decoupling capacitors are used in power supply circuits to filter out high-frequency noise and ensure a stable voltage supply for sensitive components. Example: in digital circuits, decoupling capacitors help reduce noise caused by switching transients and maintain stable voltage levels for microcontrollers and logic gates. Microcontroller power management. Decoupling capacitors stabilize the voltage supply to microcontrollers and other digital components, preventing noise and ensuring reliable operation. Example: in a microcontroller-based system, decoupling capacitors placed near the microcontroller's power pins prevent fluctuations that could affect performance. High-frequency signal decoupling. Capacitors are used to decouple high-frequency signals in RF circuits, ensuring that the high-frequency components do not interfere with other parts of the circuit. Example: in RF amplifiers, decoupling capacitors prevent unwanted high-frequency noise from affecting the performance of the amplifier. Power conditioning and switching regulators. Decoupling capacitors are used in switching regulators to filter out high-frequency switching noise and stabilize the output voltage. Example: in a buck or boost converter, decoupling capacitors smooth out voltage fluctuations and reduce noise caused by the switching elements. Advantages of capacitors in coupling and decoupling. Improved signal integrity. Capacitors ensure that AC signals are transmitted without distortion and that noise is filtered out, maintaining clear and stable signal paths. Enhanced stability. Decoupling capacitors provide stable voltage levels and reduce noise, improving the reliability and performance of electronic circuits. Versatility. Capacitors can be easily sized and placed to match the needs of various coupling and decoupling applications. In summary, capacitors play a vital role in coupling and decoupling by managing signal transmission and power stability. Coupling capacitors ensure proper signal flow between circuit stages, while decoupling capacitors maintain stable voltage levels and reduce noise, contributing to the overall performance and reliability of electronic systems. Tuning is an important application of capacitors in electronic circuits. Capacitors are used to adjust and select specific frequencies, enabling fine control over the behavior of various devices. Here's an in-depth look at how capacitors are used for tuning and their applications. How capacitors are used for tuning. Principle: frequency selection. Capacitors can be combined with inductors to create LC circuits, where the resonant frequency of the circuit is determined by the values of the inductance, L, and capacitance, C. The resonant frequency, 0, F, 0, of an LC circuit is given by 0 equals 1, 2, pi, F, 0 equals 2 pi, LC, 1, where 0, F, 0 is the resonant frequency, L is the inductance in henries, C is the capacitance in farads. Adjustable capacitance. By varying the capacitance in a circuit, you can change the resonant frequency and thus tune the circuit to select or reject specific frequencies. Applications of capacitors in tuning. Radio tuning. Description: capacitors are used in radio receivers to select specific radio frequencies from a broad spectrum of signals. By adjusting the capacitance, the receiver can tune into different radio stations. Example: in an AM or FM radio receiver, variable capacitors, or tuning capacitors, adjust the resonant frequency of the circuit to match the frequency of the desired radio station. Frequency modulation, FM, transmitters, and receivers. Description: capacitors are used to tune circuits in FM transmitters and receivers, allowing for precise frequency adjustments and signal stability. Example: in an FM transmitter, capacitors in the oscillator circuit determine the carrier frequency of the transmitted signal, while in the receiver, they help tune to the correct frequency. Crystal oscillators. Description: capacitors are used in conjunction with crystal oscillators to fine-tune the frequency output. The crystal provides a stable reference frequency, while the capacitors adjust the final frequency. Example: in quartz crystal oscillators used in watches and precision clocks, capacitors are used to trim and stabilize the oscillation frequency. filtering and resonance circuits. Description: capacitors are part of LC circuits used for filtering and resonance applications, where precise frequency selection is required. Example: in audio equalizers, capacitors help create bandpass or bandstop filters to adjust the frequency response and improve sound quality. Automatic frequency control, AFC, systems. Description: capacitors are used in AFC systems to automatically adjust the tuning of a circuit to maintain a stable frequency. Example: in television tuners, AFC circuits use capacitors to keep the receiver locked onto the correct channel frequency, compensating for drift or variations. Phase-locked loops, PLLs. Description: capacitors are part of the tuning networks in PLL circuits, which are used to synchronize a generated signal with a reference signal. Example: in communication systems, PLLs use capacitors to adjust the phase and frequency of the output signal to match the input reference signal. Adjustable filter networks. Description: capacitors and adjustable filter networks allow for tuning the filter to pass or block specific frequencies. Example: in communication equipment, adjustable filters are used to select the desired signal frequency while rejecting unwanted frequencies. Advantages of capacitors in tuning. Precision. Capacitors can be finely adjusted to achieve accurate frequency tuning, essential for high-performance electronics. Flexibility. Variable capacitors allow for easy frequency adjustments in various tuning applications. Stability. Capacitors help maintain stable and consistent frequency characteristics in tuning circuits. In summary, capacitors are integral to tuning applications in electronic circuits. They allow for precise frequency adjustments in radios, transmitters, receivers, and oscillators, and are crucial for maintaining stable and accurate frequency performance in various electronic devices. Voltage regulation is a key function of capacitors in electronic circuits. Capacitors help maintain stable voltage levels, which is crucial for the reliable operation of electronic components and systems. Here's a detailed look at how capacitors are used for voltage regulation and their applications. How capacitors are used for voltage regulation. Principle: stabilizing voltage. Capacitors can smooth out voltage fluctuations by storing and releasing charge. When there are changes in the load or input voltage, capacitors absorb or provide charge to keep the output voltage stable. Filtering ripple. In power supply circuits, capacitors filter out AC ripple and noise from the DC output, ensuring a steady and clean voltage supply. Types of voltage regulation. Filtering capacitors. Description: capacitors smooth out fluctuations and reduce ripple in the output voltage of power supplies. Application: in a rectified power supply, capacitors are placed after the rectifier to filter out the AC ripple and provide a smoother DC output. Decoupling capacitors. Description: capacitors are placed near the power pins of integrated circuits, ICs, to stabilize the voltage supply and filter out high-frequency noise. Application: in digital circuits, decoupling capacitors prevent voltage spikes and noise from affecting the performance of microcontrollers and other ICs. Voltage regulation circuits. Description: capacitors are used in conjunction with voltage regulators to maintain a stable output voltage. Application: in voltage regulator circuits, capacitors help stabilize the output voltage by smoothing out variations and ensuring consistent performance. Applications of capacitors in voltage regulation. Power supply filtering. Description: capacitors smooth out fluctuations and reduce ripple in the output of power supplies. Example: in a switching power supply, capacitors filter out the high-frequency noise generated by the switching process, providing a stable DC voltage to the load. Regulated power supplies. Description: capacitors work with voltage regulator ICs to maintain a steady output voltage despite variations in input voltage or load. Example: in a 7805 voltage regulator circuit, capacitors are used to filter and stabilize the 5V output, ensuring reliable operation for electronic devices. DC-DC converters. Description: capacitors are used in DC-DC converters to filter and stabilize the output voltage. Example: in buck or boost converters, capacitors smooth out voltage variations and reduce noise, ensuring a stable output voltage for sensitive electronics. Power conditioning in analog circuits. Description: capacitors stabilize the voltage supply for analog circuits, reducing noise and ensuring accurate signal processing. Example: in operational amplifier circuits, capacitors help maintain a stable voltage supply, improving the accuracy and performance of the analog signal processing. Voltage reference circuits. Description: capacitors are used to stabilize voltage reference circuits, ensuring consistent and accurate reference voltages. Example: in precision voltage reference circuits, capacitors reduce noise and maintain stability, providing accurate reference voltages for measurement and calibration. Electromagnetic interference, EMI, filtering. Description: capacitors filter out EMI and RFI, radio frequency interference, to prevent voltage fluctuations and ensure stable operation. Example: in EMI filters, capacitors work with inductors to block high-frequency interference and stabilize the voltage supply. Battery management systems. Description: capacitors are used in battery management systems to smooth out voltage variations and improve the stability of the power supply. Example: in rechargeable battery packs, capacitors help manage voltage fluctuations and ensure consistent power delivery. Advantages of capacitors in voltage regulation. Improved stability. Capacitors help maintain a stable voltage supply, reducing fluctuations and ensuring reliable operation of electronic components. Noise reduction. Capacitors filter out noise and ripple, improving the performance and accuracy of electronic circuits. Flexible design. Capacitors can be selected and sized to match specific voltage regulation needs, providing flexibility in circuit design. In summary, capacitors play a critical role in voltage regulation by smoothing out fluctuations, filtering noise, and stabilizing output voltage. They are essential for ensuring the reliable performance of power supplies, voltage regulators, and various electronic systems. Energy conversion is another important function of capacitors, involving the transformation of electrical energy into other forms of energy or the modulation of electrical energy within electronic systems. Here's an overview of how capacitors are used in energy conversion and their applications. How capacitors are used for energy conversion. Principle: electrical to mechanical energy. Capacitors can convert electrical energy into mechanical energy by utilizing the electric field's force to drive mechanical components. Electrical to electromagnetic energy. Capacitors are involved in creating and manipulating electromagnetic fields in certain applications. Applications of capacitors in energy conversion. Capacitive touchscreens. Description: capacitors are used to detect touch input by measuring changes in capacitance caused by the presence of a finger. How it works: when a finger touches the screen, it changes the capacitance at the point of contact. The change in capacitance is detected and translated into touch input. Example: capacitive touchscreens in smartphones and tablets rely on this principle to provide touch sensitivity and gesture recognition. Ultrasonic transducers. Description: capacitors convert electrical signals into mechanical vibrations, which are then used to generate ultrasonic waves. How it works: in ultrasonic transducers, a capacitor, often in combination with a piezoelectric material, vibrates when an electrical signal is applied, creating ultrasonic sound waves. Example: in medical ultrasound imaging, ultrasonic transducers generate and detect sound waves for imaging internal body structures. Power factor correction. Description: capacitors are used to correct the power factor in AC power systems, improving the efficiency of power conversion and reducing losses. How it works: by adding capacitors to an AC circuit, the phase difference between voltage and current is adjusted, improving the overall power factor. Example: in industrial settings, capacitors are used to correct the power factor of motors and other inductive loads, enhancing the efficiency of the power system. Energy storage for high-power applications. Description: supercapacitors, or ultracapacitors, store large amounts of energy and release it quickly, providing bursts of power in applications requiring rapid energy delivery. How it works: supercapacitors store energy electrostatically and can deliver high power densities for short durations. Example: in electric vehicles, supercapacitors assist with quick acceleration and regenerative braking by providing and absorbing rapid bursts of energy. Capacitor discharge flashers. Description: capacitors store electrical energy and release it in a burst to create bright flashes of light. How it works: in flash devices, a capacitor charges up and then discharges rapidly through a flash tube, creating a bright flash of light. Example: in camera flash units, capacitors store energy and provide the necessary burst of light for photography. RF and microwave energy conversion. Description: capacitors are used to create and manipulate RF, radio frequency, and microwave signals in communication systems. How it works: capacitors are used in resonant circuits, filters, and impedance matching networks to convert and control RF and microwave frequencies. Example: in RF amplifiers and communication systems, capacitors help in tuning and filtering signals to achieve desired frequency characteristics. Inductive energy storage and conversion. Description: capacitors are used in conjunction with inductors to store and convert energy in circuits, such as in resonant or switched-mode power supplies. How it works: capacitors and inductors together store energy in the form of electromagnetic fields and can convert it between electrical and magnetic energy. Example: in a resonant converter circuit, capacitors and inductors work together to convert and regulate energy efficiently. Advantages of capacitors in energy conversion. Fast response. Capacitors can charge and discharge quickly, making them suitable for applications requiring rapid energy transfer. High power density. Supercapacitors provide high power densities for applications needing bursts of energy. Versatility. Capacitors can be used in various energy conversion scenarios, from touchscreens and imaging to power factor correction and energy storage. In summary, capacitors play a crucial role in energy conversion by transforming electrical energy into mechanical, electromagnetic, or other forms of energy. They are essential in applications such as touchscreens, ultrasonic imaging, power factor correction, high-power energy storage, and RF signal manipulation, contributing to the efficiency and functionality of modern electronic systems. These functions highlight the versatility and importance of capacitors in a wide range of electronic applications, from basic power supply filtering to advanced signal processing and energy storage.